Well, howdy students. This is going to be a video that covers hydrated compounds. After this video, you're going to watch another video that shows efflorescence, deliquescence, and desiccants in a part 2 of our lab. So the first thing we need to know, what is a hydrate? What is hydration? And specifically, what is water of hydration? So the first thing we're going to talk about is water of hydration, which is water that's inside of a crystal compound. So some compounds are special that they can actually have water bound to their crystal structure. So for instance, copper 2 sulfate is dissolved in water, and then when the water is allowed to evaporate, we form a compound, a hydrated compound, that is called copper 2 sulfate pentahydrate. So here's the reaction for that. We start out with the ionic compound. This is copper 2 sulfate, and we add water. In fact, we could add excess water here, but this specific equation shows the 5 waters that are eventually going to become the hydrate. And so you'll notice that the plus sign becomes this dot, which means integrated. So this compound has been integrated with water, and 5 of them specifically. Different compounds have different numbers of hydrate molecules on them. So a hydrate is a compound that contains water of hydration. So water of hydration, hydrates, you can call them either one. The picture to the right, if we look towards the back, you'll see there's our copper 2 sulfate. And then on top, you'll see all these water molecules bound to the crystal structure. When cobalt 2 chloride is dissolved in water and the excess water is allowed to evaporate, we form cobalt 2 chloride hexahydrate. So here it is, cobalt 2 chloride. It's a blue compound, but when we add water and let it evaporate, we form a hexahydrate, and it actually has this distinct dark red, almost maroon color. So hydrates can have different properties of their individual compound. In the hydrate, in the hydrate copper 2 sulfate pentahydrate, how many water molecules would be present if we had 3 formula units of this compound? Well, if you have 3 formula units, and there's 5 waters within the structure, we would distribute that 3 and say that there are 15 total H2O molecules within the compound, within 3 of them. So now we're going to look at naming hydrates. To name a hydrate, we use the following. They are named by giving the name of the salt, followed by a prefix that stands for the number of water molecules associated with one formula unit of the salt. So first thing you got to remember is how to name the salt. So I may point you to your ion chart if you need help naming ionic compounds. And then we may need to review the prefixes: mono, di, tri, tetra, penta. That's 1, 2, 3, 4, and 5. And then 6, 7, 8, 9, 10. We're going to have hexa, hepta, octa, nona, deca. So if I'm naming this one like I named earlier, we have copper, which is special. Copper can be 1 or 2. And then we have a polyatomic ion here, which is sulfate, which has a 2- charge to it. So this would be copper 2 sulfate, because the 2 plus canceled out the 2- on sulfate. If it was copper 1, we would have Cu2SO4. And then with the prefix for 5, that would be penta. And then we just add the name hydrate. There is no space between the prefix and hydrate, but there is a space between the compound and the hydrate. Okay, now we're going to calculate the percent hydration, or what we call percent water in the compound. So the equation goes like this. To find the percent of water within a hydrate, you need the mass of water specifically over the total mass. So we're going to find the amount of water percentage-wise within this compound. And I do see 5 waters, so we're going to take 5 waters and divide it by the total mass. So we're going to have to bring back the concept of molar mass, which means we're going to need our periodic tables. So I'm going to find the molar mass of copper 2 sulfate. I got 1 copper, 1 sulfur, and then 9 oxygens. We're taking into account the 5 waters here and the 4 oxygens here, which gives for a total. And then there's 10 hydrogens because 5 times 2 is 10. So right now we're finding the total mass. Here are the molar masses. Copper is 63.5, sulfur is 32.1, oxygen is 16.0, and hydrogen is 1.0. I want to remind you that we round molar masses on the periodic table to the nearest 0.1 gram per mole. And that's what we see here. When we total everything up, our total mass is 249.6. And then I also need to find just the mass of H2O. So here I'm just looking for the waters. So the molar mass of water is 18. And you'll notice that I'm multiplying it by 5 down here because I have 5 water molecules, which gives me 90 grams. So I'm going to plug it into my equation. I will be multiplying by 100. And this will be on the next slide here. So pause if you need to finish writing. So the equation is mass of H2O over the total mass of the hydrate times 100. So the total mass for the water was 90. And the total mass for the whole hydrate, the whole compound with water included, is 249.6. Final answer, 36.1% water. In part 2 of the lab, we're going to observe 3 different concepts: efflorescence, deliquescence, and then also a desiccant. Efflorescence is the process in which a hydrated compound loses water to its surroundings. It occurs when a substance has a vapor pressure higher than that of water. The water is forced out of the compound. Some hydrated compounds can effloresce and will form anhydrous compounds. That word, anhydrous, means without water. It's the opposite of water. So I have my students draw on a picture on their notes. Compound that has a higher pressure than its surroundings will actually force out the H2O in a process we call efflorescence. The opposite of that would be deliquescence, process in which an anhydrous or somewhat hydrated compound gains water. So again, anhydrous without water is going to gain from the surroundings. So this occurs when the solution has a vapor pressure lower than that of the water in the air. Some anhydrous or somewhat hydrated compounds will deliquesce to form hydrated or more hydrated compounds. Water is gained. So I have my students, once again, draw another bubble with the compound in it, and I want them to show that deliquescence is when water enters the compound. And the way that I look at it, deliquescence reminds me of the word quenching, which means to drink, or to hydrate, which means you're taking on water. And the last term would be a desiccant. A desiccant is something that's hygroscopic, meaning it absorbs water, and they can be used as drying agents. Now, desiccants aren't necessarily hydrates. They fall into their own category. They do absorb water, and they are used as drying agents, but they're not necessarily a hydrated compound. So, example that we see in everyday life would be a silica gel packet. These are used in merchandise when they're shipping to keep things dry because they absorb water. The reason we don't eat them is because silica gel is carcinogenic, which means it gives the ability to cause cancer within your body. Sodium hydroxide is a desiccant, and it becomes a solution. It dissolves itself. So if we leave this sitting out, what we're going to find is that those little pellets kind of become puddles. They absorb the water, and they don't hold their structure.